We know that everything around us is made up of the 118 elements on the periodic table. Not everything is in its elemental form. We've learned about how atoms come together to form bonds and create compounds. And now we know that certain compounds can be mixed together, and depending on what the compounds are, they could either appear as a solution or a heterogeneous mixture. And literally everything around us is organized in one of those ways. And so everything has a name. And this video is going to show you an introduction to how some of the smaller substances, in terms of scale of bonding, are named. And to highlight a few of those ways, I chose the example of Gatorade. Now, if you look at the back of a Gatorade bottle, you'll see all the ingredients there. And this is true about pretty much every food that you can buy. If it has multiple ingredients, they're required to provide you an ingredients list. And so here in Gatorade, the first ingredient is water. And water is a common name. A lot of substances that are used frequently or are too big to name systematically are named with common names that, well, make it a lot easier to say. And so right away, the first three ingredients in Gatorade, actually, water, sugar, and dextrose, are common names. And common names can be used for all sorts of compounds: ionic, nonpolar, covalent, and covalent. And we know that water's formula is H2O. And I said earlier that we use common names for substances for a lot of reasons. One of those being, if the chemical formula is so long, well, that's not really the case with water. In fact, you may refer to water as H2O every once in a while. But sugar, on the other hand, sucrose, has a longer formula: C12H22O11. It's much easier to say sugar or sucrose than it is to list the formula. And dextrose's formula is C6H14O7. And here we're seeing why they came up with a common name. It's a lot easier to say sugar and dextrose. And although there are a lot of common names in this list of ingredients for glucose, a lot of them follow a system that scientists developed to name compounds. And we'll move through those in the next slides. The first type of compound that I'd like you to learn how to name are type 1 compounds. Those compounds are what we call binary ionic compounds, where the metal comes from group 1, 2, or 13. And an example of that is salt, sodium chloride. And sodium is in group 1, and chloride is from group 17. And the fact that sodium comes from group 1 puts it into this type 1 category. And that'll make more sense as we work through the different types of compounds. And of course, the formula for sodium chloride is NaCl. And one thing I'd like to notice, or I'd like you to notice before we move too far, is that the ending of the compound name has been changed to "ide." And that's how we know it's a compound. The nonmetal, the anion, the ending is changed to "ide" in most of these groups of compounds. Another example of a type 1 compound that we've seen this year is magnesium oxide. Magnesium is in group 2 of the periodic table, making it fit into this type 1 group. And the last example, grab something from group 13 here, is aluminum chloride. And in terms of naming these type 1 compounds, the cation, the positive ion, retains its element name: sodium, magnesium, aluminum. While the anion, the nonmetal ion, has the ending changed to "ide": chloride, oxide, and chloride. The second type of ionic compounds that I'd like you to learn is type 2. Type 2 compounds are, again, binary ionic compounds, meaning they have two things in them, a cation and an anion, except in this group, the metal is a transition metal. And the example that I'd like to use first here is iron 2 oxide. Now you might be thinking, well, what's that 2? Well, the reason this group of compounds has a special naming system is because they include transition metals. And a lot of the transition metals on the periodic table exist in nature in multiple charges. And what do we mean by that? Well, we have iron here, and an example of one iron compound, where the 2, what's in parentheses, tells you the charge of the iron ion in the compound. And the iron ion here is +2. And we know that oxygen is in group 16, and all of those form -2 ions. And so the formula for this compound would just be FeO. But we see here that iron actually can exist in many different charges. And the second example to use iron would be iron 3 oxide, where the charge of that iron ion in this compound is +3, and oxide is always -2, which would make the formula for this compound Fe2O3. And what we see now here is that we have two iron oxide compounds, but in order to distinguish between them, because they are very different, right? The ratios of iron to oxygen are different in each. In order to distinguish them from each other, this system of naming had to be developed to indicate the charge of the ion in the name. And so we've got two examples here, iron 2 and iron 3 oxide. And this applies to a lot of transition metals. What you see here isn't an exhaustive list of the transition metals that have multiple charges, but it's a great deal of them. And so for this particular type of compound, it's a valuable skill to be able to reverse engineer a compound into a name. For example, let's choose the compound Cu2O. We know this compound has copper in it, we know this compound has oxygen in it, but the question is, what is its name? Well, the fact that it's a transition metal sort of alerts us that it needs a Roman numeral in its name. And we just got to find out what that is. We see here in the formula that, again, it contains copper and oxygen always has a -2 charge. And so if the net charge of the compound has to be 0, and there are 2 copper ions that have to account for a total of +2, that means that each one must have a +1 charge. And there are 2 of them, so 1 + 1 - 2 is 0. And so we've reverse engineered this formula to determine what the charge of each of those copper ions is, and we determined that it was copper 1. And so the name of this compound would be copper 1 oxide. The third type of compound that I'd like you to learn, or at least be able to recognize, are these type 3 compounds. They're binary covalent compounds. Types 1 and 2 are ionic, this one is covalent. And one of the most common examples of a type 3 compound is carbon dioxide. And now if we analyze the name of this formula, we see some things in common with the other types. The first element in the formula retains its element name, carbon. The second element in the formula does not retain its element name. If we were to name it with just using the element name, it would just be carbon oxygen, but that doesn't really tell us much. What I'd like you to notice here are 2 things. One, that the ending of that second element is "ide," just like in the type 1 and type 2 compounds. But there's also something unique about this second part of the name that is also unique to the type 3 compounds, and that's this prefix here, di. And there's a series of numerical prefixes that we can use to let us know how many of each type of element are in this formula. So carbon dioxide. If there isn't a prefix like di or tri or tetra, we can assume that there's just one of those atoms of that element in the formula. In this case, that's carbon. The second element has that di prefix, which if we look over here, means 2. That says that there are 2 oxygen atoms in this compound. And now that we have the whole formula of carbon dioxide, that hopefully looks familiar. And now the second example that I'd like to use for the type 3 compounds is one that I'm sure you're familiar with, H2O. And now we know that this compound has a common name, water. But because it's also a covalent compound, it has a systematic name. And now let's reverse engineer this using these prefixes. So the first element is hydrogen, and there are 2 of them, and so we would use that prefix di, and that would become dihydrogen. And the second element in water's formula is oxygen, and there's only 1 of them, and so it would require the mono prefix and become monoxide. And now you may be asking yourself the question, all right, so in water's formula there's only 1 oxygen and we use the mono prefix. But in carbon dioxide, there's also 1 carbon, but we didn't use the mono prefix. Typically, if there's only 1 of the element, and it's the first element in the compound, we don't use the prefix. But if that element with only 1 atom in the compound is second, we do use the prefix. The last of the categories of substances that I'd like you to be able to name and write formulas for are compounds with polyatomic ions in them. And that's a broad category, but every compound has a polyatomic ion in it. And we just looked at type 3, type 2, and type 1. You could call this type 4 if you want to, but I don't think that's really appropriate, and hopefully you'll see why. So just a refresher, a polyatomic ion, if we analyze the name, or that word, poly means many, atomic means, well, atom, and ion, well, that means ion. And so what a polyatomic ion is, it's a many atom ion. An example of this is carbonate. It's an ion because it's charged, but there are many atoms in it. In fact, there are 4 atoms in this ion. And I think it would be helpful to see the Lewis structure for carbonate. So here's carbonate. A lot of the times we see these polyatomic ions represented with brackets, and then the charge of that polyatomic ion outside the brackets. And polyatomic ions walk, talk, eat, and sleep just like monatomic ions. They travel together, they are charged particles, they're just bigger. And so there are many, many, many polyatomic ions. A list of polyatomic ions is readily available on the internet. I'll certainly give you one to work with, and you can look that up if you're interested. And so to understand how compounds with polyatomic ions in them are named, let's look at some examples. The first example is sodium acetate. Sodium is Na, and acetate is C2H3O2 with a -1 charge on it, meaning the formula for sodium acetate is NaC2H3O2. And what I'd like you to see in here is the sodium and the acetate. And I chose not to call this type 4 because the naming for compounds with polyatomic ions in them depends on the metal ion. And since sodium is a type 1 ion, because it's from group 1, 2, or 13, it doesn't require a Roman numeral. We just see here that the name is sodium, the name of the first element, and acetate, the name of that polyatomic ion. Second example, tin 4 nitrate. Now we can see already that this one has a Roman numeral in it, and that's because the metal in this compound is a transition metal. And so the formula for tin, or the symbol for tin rather, is SN, and the formula for nitrate is NO3 with a -1 charge. And in order for the net charge of this compound to be 0, there has to be 4 of those nitrates in the formula. And the way we do that with polyatomic ions is that we wrap the polyatomic ion in parentheses and indicate how many of those ions are in the formula by putting a subscript outside the parentheses. And so if we know there has to be 4 of these nitrate ions, we put a 4 there and complete it with the anion tin. So the full formula of tin 4 nitrate would be SN NO3 4, and it would look like that. And finally, I'd like us to reverse engineer a formula just so that we can review how these compounds with polyatomic ions are named. We've got CaSO4. So the first piece of that formula is Ca, that stands for calcium. Calcium's in group 2. And so because it's a type 1 metal, the name of this compound does not need a Roman numeral. And the second piece of the formula, SO4, that polyatomic ion is sulfate. And that's the name for this compound, calcium sulfate. Let's do one more. Let's reverse engineer one of these compounds with a transition metal in it. This formula with a transition metal in it reads MnClO3 3. We can see that the tricky part is the transition metal. We don't necessarily know what charge it is. So remember back in the type 2s, we focused on the anion and determine its charge, and then use that to help us determine the charge of the transition metal. So here, the polyatomic ion in question is chlorate, and its formula is ClO3 with a -1 charge. And that charge information is on that list of polyatomic ions that I mentioned earlier. And so we know that if the charge of each of those chlorates is a -1 and there are 3 of them, the total charge of the anions is -3. And because there's only one of the cations, the charge of that cation must also be +3 because there's only one of them. And so again, if we've got 3 of those chlorate ions, each of them has a -1 charge, that manganese has to have a +3 charge to balance out the negative charge. And so now that we know the charge of this manganese ion, we can name this compound. And so it starts with the element name for the metal, manganese, and its charge, +3, means that this name needs the Roman numeral 3. So it would read manganese 3 chlorate. And that's a wrap.